So we are discussing structure. So starting from the atomic structure, we can have arrangement of protons, arrangement of electrons, arrangement of neutrons. So if we see the electronic structure, so only the number change in the proton, neutron, and electron. Means every time number of protons, number of electrons, and number of neutrons will be equal. So if this number changes, suppose hydrogen is having one proton, one neutron, and one electron. And if we add, or if there are two protons, two electrons, or two neutrons, so it will be a altogether different element, helium. So hydrogen has a different property, helium has a different property, and all these particles, protons, neutrons, and electrons, are having equal weight and sizes. Okay, so this is well known. Means if there is a change in number of electrons, protons, the element will change, and that's how our periodical table has been generated. Okay. Then another is energy band structure. So energy band structure basically defines the behavior of materials, whether they are insulator to heat and electricity, whether they are semiconductor, and whether they are conductor of electricity and heat. So this structure is explained by three different bands. One is conduction band. So if any electron is present in this band, then that is supposed to be conductor of heat and electricity. And there is a valence band. So valence band means outermost electrons will exist in this. So this is the energy level of valence electrons. So depending upon the band gap between conduction band and valence band, these materials are defined. So insulators will have a very big band gap, and semiconductors will have very less band gap, or sometimes they are doped with another element which will have a valence overlap of their conduction and valence band. And there is another band which is filled band. So that is not taking any part in all these interactions. So conductors will have overlapping valence band, this outermost band energy level and conduction band. So some excitation, if external excitation will be provided in terms of heat or electricity, and there will be a start of flow of electrons by conducting heat and electricity. There is another thing, very specialty in case of carbon. Some of the elements they will have a different crystal structure, like a carbon. So it can have a graphite, it can have a diamond. So this is due to hybridization of their one S and other P shells of configurations. So if one S shell and two P shell they do hybridization, so there will be sp2 hybridization, means and it will generate a three shell. So basically one atom of carbon is connected with other three atoms here. So this is called as sp2 hybridization, which is available in case of a graphite. And in case of a diamond, 1s and 3p shells are taking part in hybridization. So here we can see one carbon atom is connected with another four carbon atom. So this is a sp3 hybridization. So see, if there is a change in hybridization, altogether two different type of materials. Means graphite is good conductor of say heat, and some we can conduct some electricity as well. It is a very soft. It is a dark. You can say gray or graphitic in color. And carbon, when it takes a form of a diamond, it is very hard, and it has a melting point very high again, and it is a brittle, it is a transparent. So you can see how the hybridization also can bring a change in material properties. So this is due to the hybridization of say electronic shells. Then there is another structure which is a magnetic domain. So unmagnetized and magnetized. So here you can see a random direction of these domains, and after magnetization they will have same domain. So in case of magnetic materials, this magnetic domain, this kind of structure is very important. Then we are considering the crystalline material. So depending upon the permutation and combination of three sides along x and y and z axis. The dimensions are the length along x, y, and z axis is normally represented by A, B, C. When these are equal, and when the angle between x, y, y, z, and zx, that is alpha, beta, gamma, is equal, and that is equal to 90 degree, we can get a cubic structure. So likewise, naturally, if we consider the geometrical space, we can have these seven types of crystal systems. Means apart from these, there is no any combination is available. So we can have a tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, rhomboedral. So if we want to see the transformation, is if how cubic can generate a rhomboedral. So this particular symbol is called as a skew operation or skew transformations. Skew means one corner of this cube and diagonally opposite of this cube. If they are stretched, so it will generate a rhombohedral. So cubic one skew operation can generate a rhombohedral, and from cubic you can see there is two sides are equal, and third side or length along that z-axis is different. So both are represented. A and B are represented here. A and C is represented separately, and all the angles are 90 degree. Okay. And orthorhombic is basically all sides A, B, C are different, and all angles are 90 degrees. So if we do one skew operation on tetragonal, we can get a hexagonal. Hexagonal unit cell you can see here. So hexagonal unit cell you might have confused with this, but this is not a unit cell. So this structure will have having a 3-unit cell, you can see. So all these conditions of say hexagonal are met here. Means A is equal to A3, means all three sides are equal. Means A1 is equal to. So this is a basically four coordinate system. So and you can get here three coordinate system here. So we are not going that much in detail in a crystallography here, and angles are 90 and 120. So so next transformation or next from orthorhombic with one skew operation, you can get a we can get a, monoclinic structure, and then another skew operation you can get a triclinic structure. So these are the all possibilities we can have in crystal systems, and which is also confirmed experimentally. Then this is a arrangement. So actually, so these are unit cells and atoms are sitting at the corner. So this is also only the representation. Actually, atoms are bigger, and so they are as good as touching to each other. Means this kind of distance will not be there. There will be very less distance. I will show that how they are sitting next to each other in case of stacking. So here the point of I want to tell. So these are the Bravis lattice. So Bravis lattice are basically say uh, actual combinations which are available in a nature. So it is depending upon the extra atom which is sitting. If there is a extra atom which is sitting, then this lattice point or regular sites of the atom. So at the face, so it is called as face-centered cubic. So it is at the center of the face, and there are the six faces. So that means six atoms are sitting on the six faces of this cube, and the this extra atom, which is say uh, means half which is lying in this unit cell, and half will be lying in the next unit cell. And then body centered cubic, so there will be one atom which will be sitting inside the cube of this. So then simple tetragonal, body centered tetragonal, hexagonal, simple orthorhombic. So depending upon say extra atom where it is sitting, you can see the body centered, base centered, face centered, simple monoclinic, rhomboidal, triclinic. Okay, these are the 14 types of Bravis lattice which are grouped in a 7 crystal systems. Then coming back to metals, metals are having these three types of closed pack structures. So closed pack structures means simple cubic, face centered cubic, and body centered cubic, hexagonal. So this is simple cubic. So if extra atom is sitting at the face, so that will be FCC, face centered cubic, and body centered cubic is one atom is sitting inside this cube, then that is a body centered cubic. And hexagonal close packed SCP structure will be, so these are the three unit cells of hexagonal type of crystal structure on its cell, and at body center of each unit cell there is one atom sitting. So all these three atoms are sitting like this. So here this type of structure is formed. So it is called as hexagonal close pack structure. So then this hexagonal close pack structure is made by AP type of stacking, and see this cubic structure is FCC structure is made by ABC type of stacking. So what is this stacking? So this is how actually atoms are sitting. So if A is this first layer, and second layer which is sitting at this say center space between these three atoms of first layer, So that is, so next will be sitting at here and another will be sitting like this. So this is A position, this is B position. If next layer is again coming just like this green layers, so that will be again A types. And further next to if come means fourth layer, if say be like a B type of stacking, then that will be AB type of stacking. And here basically in case of ABC, AB stacking is already there. So so there is another space or another option like here. So here if third layer is sitting here, so it is shown here in a blue color ball or circles. So this is called as ABC. And if this stacking is repeated after that, so that is called as ABC type of stacking. So this kind of thing, if you want to understand, you need to bring a solid different color small balls, and you can put one or other, and you can understand that better than whatever is explained here. Then there are defects in crystal structure. So defect, we know as name suggests, it appears to be a negative. But by that way, in case of metal, this defects is not the negative term. So the definition of defect, crystalline defect, is basically it is a deviation from what is to be considered as ideal structure. So anything deviation from the ideal arrangement, it is called as a defect. Okay. So there are four types of defects: point defects, that is zero-dimensional defects; in line defects, those are one-dimensional defects; surface defects, those are two-dimensional defects; volume defects, these are three-dimensional defects. So vacancy, self-interstitial, interstitial impurity, substitutional impurity, Frankel defect, Schottky defect, edge dislocation. So means all these are point defects. So it is basically depending upon one atom, whether it is missing or it is occupying, or whether other element atom is coming. And then the Frankel and Schottky are basically a combination of two types of point defects. In case of line defects, there is edge dislocation, screw dislocation, and mixed dislocation. So we will be seeing only the defects which are related, which are required to understand our topic, that is structure and property. Other all defects we are not going to see here. Then the surface defects are two-dimensional defects: grain boundary, twin boundary, stacking faults, phase boundary. And volume defects are twins, precipitates, faulted region, void, cracks, thermal vibration, etc. Then important defects basically related to the processing of metals. So vacancies means one atom is missing from the regular site. So how vacancies can be generated? If we heat the metals, so basically if due to the heat energy, the excitement or the vibrations of atoms will increase, and they can leave their regular position. So this can be generated vacancy. Then alloying and heat treatment basically can generate a substitutional solid solute or interstitial solid. So interstitial basically it is not a regular site. It is the space in between two atoms, two regular atoms. Regular means corner atom of the unit cells, which is called as a regular site. So interstitial solute needs to be smaller than the parent or solvent, say atoms. And substitutional can be small, it can be big, bigger than the solvent atom. So substitute means if one say uh, atom is which is say impurity which is substituting the atom from the regular side, so that is called as substitution. So then these things are can be generated, means alloying. If we are alloying carbon to the iron, so the carbon goes in the space like interstitial. If we are adding a chromium to iron, so it can take a regular site, so it can be a substitutional solute. So then edge dislocations helps in a plastic deformation. So edge dislocation, what is edge dislocation? Edge dislocation is basically you can say, I just try to draw something. So if there are a slice of bread, and if there is an extra half slice which is added in that slice, so along this point, so this is a three-dimensional structure. Okay, so there will be along this line which is perpendicular to this plane. So above this atom and below this atom, the structure of crystal which is perfect. Only there is a problem with this atom. So all these atoms connect together, make a line which is called as edge dislocation. So this is extra half plane, and this is going to help in a plastic deformation. So if we deform the material, then there will be a multiplication of dislocation. So these defects can be, means this line defect can be generated. So this is a zero-dimensional. Vacancy is a zero-dimensional. This is zero-dimensional. This is a one-dimensional, and this is a two-dimensional. Two-dimensional surface defect. So grain boundaries. So grain boundaries are basically within a grain. Structure is like a single crystal, or it is like a crystal. And what is the difference between one grain and another grain is basically orientation. So suppose this is having this orientation, and this is having this orientation. So if the orientation between these two, or the angle between these two orientation is more than 15, so it will make a full boundary, and that is called as a grain boundary. Full region will be there, and there will be some atoms which are sitting across the grain boundary. So they will not be either join this configuration or that. So they will be just lying as it is. So virtually it is an amorphous region. So grain size can be a so each grain will if is a kind of spherical structure, and the grain boundary region is shared by two adjacent grain, and we can change the grain size by cold working followed by annealing. So coarse grain boundary is weak, and fine grains, basically not a grain boundary. Grains are strong. Okay. So how the processing? Processing is we are heating, we are alloying, we are deforming, and heat treating. So these are the processes, and how the defects are generated, created, nullified. And these are basically changing the property. So if we are adding carbon to this iron, so that is solid solution, called to be solid solution. So solid solution is basically increasing the strength. Like in case of a heat treatment, we are making another phase tempered martensite, and we are doing tempering in case of steel. So that is going to make it harder. So this is how we are changing the structure and changing the properties. So this is very basic question, how metals deform. So in earlier slide we have seen that metals can deform by movement of dislocation. So dislocations are helping. So dislocation basically extra half plane is there. Extra half plane is here first, and it is moving like this. So how it moves? So all these items are not coming and making a step here like this. Okay. So first this particular bond will break. Okay, and it will make a bond with this. So what will happen? This position will be there. So virtually this uh, extra half plane has been migrated to right side by one stage. Then next stage it will this bond will form. This bond will break. Okay. So now it will be like this. So like this is coming. So this is same explanation in two-dimensional, and we can see the caterpillar. So it has so many legs, but it is not say taking all legs up at a time. So it will be impossible to do him because it has not that much strength, or it cannot take all legs up and jump like this. So it is producing a kink in its body, and that kink is transforming here. So that kink is basically uh, here. This kink is basically a dislocation. So likewise, the metals are forming. So metals deform in a slip plane, slip direction across the slip plane. So this is one of the mechanisms slip, and another is a twin. So this is how metals deform, and this is the specialty of metals that is making metals more useful than other materials like ceramic or plastics or composites. Then coming to properties. So properties, we can see there are different properties like density, then tensile strength, then stiffness, then resistance to fracture. So we can see metals are everywhere. Metals are good in case of a density. So it is not good, but okay. Sometimes it is good, sometimes it is bad. In case of tensile strength, metals are having a high. So here composites are coming in picture, and in case of this stiffness or Young's modulus, metals are having good, and composites are here coming. Ceramics are coming down, yeah, because those are porous. And resistance to fracture toughness also, metals are good. These are dense. These are not having a porosity. These are having porosity, and these are not having that much strength. And composites are again here coming. So metals are having a competition mostly if there is a strength kind of thing. Uh, Strength is a criteria, so metals are the superior must. The properties are tested by many mechanical testing methods like hardness test, tensile test, compression test, flexural strength, many fatigue test and all. So we can see the tensile test of will give a graph of load versus elongation. So earlier it is a load versus elongation. Delta L will be there, and if it is divided by original length and load means here I am writing force by original area, so that will become a stress and a strain. So it is engineering stress and engineering strain. Again, to convert that into push strain and push strain, that those are a part of mechanical behavior. So in case of engineering stress and strain, we can get a maximum tensile strength UTS here, and the breaking strength here, and somewhere here yield strength, and this is the elastic region, this is plastic region, total area under that is toughness and all that. So These are all basics we need to understand related to the properties. And as charts are basically plotted with one property like a strength with say compared to the elongation. So these are basically giving say metals are having high strength as well as high elongation, and ceramics are having a less elongation and less strength. Like this, we can select materials by using these aspect charts. So here, Young's modulus and density. So ceramics are having this here, and wood is having low dense. These are light, and composites are here. Then metals are again having heavy, and but they are having a high Young's modulus. So for a particular application, depending upon the requirement, we can use the S-based charts to find out the candidate material for given application. These are the properties of steel. So you can see there are AISI. These grades are, suppose there is 1020. So as there is a change in condition, as rolled, normalized, and aligned. So you can see there is a change in mechanical properties. UTS, yield strength, elongation, percentage RA, hardness, all these properties. So what is this? This is nothing but a processing. So if processing changes, properties will change. So what are the processing? So there can be a n number of processing. I am just giving some of the examples. Like a basic process is a casting, means heating the metal to liquid state and then pouring it into the mold. This is the basic process. So you can get a complex shape like gray cast iron, aluminum casting. A lot of then hot forging, cold rolling, hot rolling. So these are the forge component. We can see the automobile parts are, most of the parts are, engine parts are forged. So why? So they are having different specialties. Different. These are stronger. These are brittle. So why they are stronger? Why they are brittle? Then cold rolling. When to do cold rolling? When to do hot rolling? Then how to differentiate between hot working and cold working. So all these things are basically related. So there is a science behind it, and the things are made on the basis of recrystallization temperature. If working of metal is above its recrystallization temperature, so that is a hot working. And if working of metal is below its recrystallization temperature, that is a cold working. So cold rolling can be cold. It is one of the cold working. And there is another process, joining method. So joining two metal parts is basically we are liquefying metal at the joint, and so it is as good as a cast structure there, and then heat affected zone and all that grains and elongated grains, everything is then substrate. So that welding is one of the process. Then heat treatment is one of the big area of processing that we need to understand. So here example, induction hardening is given. Some shaft is there, so copper coil is there, and it is heating above its oxidizing temperature and water quenching, followed by water quenching to get a martensitic structure. So all these processing give ease of manufacturing to required shape. So suppose there is a complex shape, so we cannot make a forging, or we cannot either we have to weld. If it has to be a one part, then casting. If we can accommodate the brittleness compared to the brittleness of this, then casting has to be used. So processing give ease of manufacturing required to shape as well as control of properties of material. So forge component has a different, there is a flow of grains, and we can have stronger structure. Okay. So we'll study that, how processing defines the microstructure and properties of matter. So the casting will give a dendritic structure. So dendritic structure, see, you can see it is a macrostructure, means this mesh distance is a 400 microns. So then it will, so the characteristics of cast structure are dendritic. It is a dendritic structure. There will be a segregation of elements. It is a brittle. Okay. Then mechanical working or rot. Sometimes it is called as a rot. WROUGST. Okay. So rot structure are having elongated grains, so and hard and brittle. If it is cold work, if it is hot work, then that will be different. So this is welded structure. Welded structure will have fusion zone or weld zone, then heat affected zone. These are along, say, coarser grain, and then base metal will be there. So it will have mixed microstructure cast as well as some heat treated microstructure. Hence, properties are also mixed. So then heat treatment. Heat treatment can have many types of things, making it soft, making it hard, some portion hard, some portion soft, like this. So there are, so microstructure depends on the heat treatment. Like annealing, it will, the microstructure will be stress-free, equiax grain, and ductility will increase. So the processing defines the microstructure. It determines the microstructure, and the properties will change accordingly. So this is a very important thing we need to understand. So this is just an example, some original structure. It is cold work. So this structure, so grain size will, there will not be a much defect. The ductility will decrease, strength will increase, hardness will increase here. Okay. And cold work structure, then if we are doing heat treatments at low temperature, means below its recovery temperature, say around 250 degree or so in case of steel. And so there will be somewhat stresses will be released due to polygonization of dislocations, but hardness, there will not be much effect on hardness and strength and ductility. And then if it is heated through the recrystallization temperature, generally it is 0.3 or 0.4 melting point, then new grains will start to form. Here you can see the new grains are forming here. And if this process is complete, so it will make 100% new grains. So the complete recrystallization is, so here initial recrystallization, some more recrystallization, recrystallization is increasing here, and the partial grain growth means after that, if still we are increasing the temperature, then there will be a grain growth. And then grain growth will have good ductility, and grain size is more and hardness is low. So depending upon, see, the here two types of processes are there. One is a cold working and another is a heat treatment. There are three types of heat treatment here shown: recovery, recrystallization, and grain growth. And how the properties and how the microstructure is changing. All these three things are interlinked: structure, property, processing. This is the topic of our today's lecture. So this is just an application of materials engineering tetrahedron to steel sheets for automotive chassis. So automotive chassis, basically performance, what is the performance? So strength to density ratio, specific weight, what is the permeability? Means we want to increase in ductility as well as increase in strength. So generally, if strength increases, ductility decreases. So we want to go in this direction in case of automotive chassis material. So in composition, what is the composition? What is the synthesis? How this can be made? What is the microstructure? So all these things are basically interlinked, and we are getting the final this uh, thing as a performance. Means lightweight, high strength. So weight reduction is the major objective um, at high strength and high ductility. These are the major objectives for automotive chassis. So body, specifically sheet metals. So this is an example how different materials, whatever we have learned, there is a need or there is application in a practical. Everything, all engineering things are basically driven by commercial things. So automotive materials are how these are changing. So as I told, here strength is increasing and elongation is weak. So people have tried to develop a different steel. So first they were using mild steel, then this different grade HSLA, trip steel, dual phase, and tube like this bench and martensitic and precipitation hard and interstitial P. So like this, depending for the different applications, like some parts will have different requirement of strength and ductility. So there is a combination of materials in case of automobile. So likewise, in case of aerospace materials, so there is a fiberglass, use of fiberglass, aluminum, and this red color represents aluminum. This green color fiberglass, and the gray is a carbon laminate composite, then carbon sandwich component. This is a bluish gray, and this is the that you can see aluminum, steel, or titanium. So very small aluminum, steel, and titanium. So and then materials used by weight also given. So 50% composite, 15% titanium, 20%. So this is how in case of a higher end applications, there is a use of composite is going to increase. So these are the references or reference books for further reading. So textbook Material Science and Engineering by William Callister, and Callister's another book is there adopted by R. Balasubramaniam is then Science of in case of your not getting above. So this is second one is the latest one, and third is the Science and Engineering of Materials, Donald Ostland and Pradeep Phule. This is also a very good book, very good illustrations, and Mechanical Metallurgy by George Dieter, and Mechanical Behavior of Material by Hoshford. And there is another the reference books are two. I'm suggesting Juster Jablonski, Nature and Properties of Materials. So here thermodynamical part is explained something. In case of Callister also some thermodynamics part is explained, but in detail Juster Jablonski and Modern Physical Metallurgy by Smallman. These are the two books. And thank you very much for watching this video. I hope this video will make your life easier in case of materials and metallurgy. Thank you.